Hello everyone, and welcome to this video where I'll take you through a sample question related to this objective called Find the points on a parametrically defined curve that have a given slope. All right, so I'm at Knewton.com right now in their Knewton Alta program. Of course, I'm in the instructor version of it, so if you're a student working through it, you're going to see a little differently than I am. And here's the question I want to go over related to that given objective. Now, of course, I can see the answers here, right? I'm in instructor mode, but I want to take you through, how these came about. Now, I would also recommend that you pause the video if you have some sort of familiarity with the topic. Try to work out the question yourself, and then come back and watch me go through it just to see how you're doing, compare your work to mine, see how well you're picking up the material. All right, so in this question related to this objective, we are asked to find all points on the curve defined by the equations x of t equals t plus 2 over t and y of t equals t minus 2 over t with a slope of 2. All right, so that means find, these two equations tell me the x and y coordinates of points on the xy plane. They depend on this parameter called t. And as you change the value of t, they would trace out a curve on the xy plane that we'll see later at desmos.com. I'll go to the online graphing calculator site to show you that. So we're asked to find the points on this curve, the curve traced out by these equations, that would have a slope of 2, meaning the tangent line to that curve, right, the direction the curve is pointing in at that moment, has a slope of 2. Okay, I'm going to go some paper here. So the equations were given for the curve, right, the parametric equations, depending on parameter t, are x of t was, t plus, and then 2 divided by t. And y of t equals t minus 2 divided by t. Okay, so we want the points on the curve. They said they want the points to have a slope of 2. All right, so slope, that's the slope of the tangent to the curve. We want that to be equal to 2. Find the points where this happens. Well, another way to write the slope of a tangent line to a curve is, dy over dx. Hopefully, familiar with this notation from calculus 1. And in parametric equations, the way that this can be calculated without eliminating the parameter, to keep t involved, this dy over dx, slope of a tangent line, is equivalent to dy over dt divided by dx over dt. So it's almost as if you took the dy over dx and divided, I'll put that in quotes, divided the numerator and denominator by this dt, even though technically that's not what we're doing. There's a development for this that I'm not going to get into here. So just know this, right? In parametric form, parametric equations, this is your slope of a tangent line. All right, so we can find each of these separately from our equations that were given. So I'll start with the numerator, dy over dt, the derivative of y with respect to parameter p. So the derivative of just t would be 1. And then I could use the quotient rule for this, negative 2 over t, but this is the same thing as negative 2 times t to the negative 1 power, this term here. And then applying the power rule, this would be plus 2 times t to the negative second, which is 1 over t squared. All right, so you got 1 plus 2 over t squared for dy over dt, the derivative of y with respect to t. I'll put that in the numerator here. 1 plus 2 divided by t squared. Okay, so that's the numerator of the expression. That'll tell me slopes of tangent lines to this curve. The denominator, taking the derivative of the x equation with respect to parameter t, dx over dt. First term again, simply t, so that's just 1. And then, plus 2 over t is the same thing as, 2 times t to the negative first again. So applying the power rule, I get minus 2 times t to the negative second. So minus 2 over t squared. So I got 1 minus 2 over t squared for the dx dt, the x prime with respect to t. And that's going to go in the denominator of this expression that tells me, slopes of tangent lines dy over dx to this curve. 1 minus 2 over t squared. Okay, and I'm going to simplify this a bit. It's going to be assuming that t is not 0 right now because it's in denominators and whatnot. So let's multiply the top and bottom here just to simplify this, turn this into a non-complex fraction, multiply by t squared, and that'll be you'll require distributing. So slopes of tangent lines to this curve are represented by the following expression involving parameter t. You have t squared plus 2 in the numerator and t squared minus 2 in the denominator. So yeah, and this would give me slopes of tangent lines to my curve, the curve traced out by these equations. You just would have to know the value of the parameter at that particular point. All right. So now the next step here, the big concept, the big question was, where is this slope of the curve, slope of the tangent to a curve, going to be equal to 2? So I'm going to take my expression here for dy over dx, slope of a tangent, and we're going to set this equal to 2. All right, and I'll take this to the next page. So let's go about solving this equation for t. And then we'll take whatever values we get and plug them back into our equations to talk about the points that we're at on the curve, right? Because that was the question. The statement was find all points on the curve where the slope is 2. Right, so let's take that down here. Now I'm going to just multiply, get rid of the denominator, multiply both sides by t squared minus 2 there. So you have t squared plus 2 on the left equals, and then, 2 times this quantity, t squared minus 2. And we'll distribute the 2. It'll be t squared plus 2 equals 2t squared minus 4. And now I'll take away t, I'll get all the t squared. T's on the right, got minus t squared, and then I'll add 4. Get, things with t on the right, constants on the left. This is one of those where you could solve. This is a quadratic in t, so I could solve it with the square root property, right? There's t in a square, but no t's outside the squares, right? So we got 6 equals, and then just t squared. So the solutions here are, and I'll write them separately. T could be, positive square root of 6, or t equals negative square root of 6. Both of these would satisfy this equation. Now, I'm not done yet. These are just the values of the parameter that take me to the location on the curve where the slope would be 2. The slope of the tangent would be 2. So now I want to find these points, right? The x and y coordinate at these particular values of t. And so going back now, here were the parametric equations up top. Right. So start with when t equals square root of 6. So the value of x when t equals the square root of 6 is the square root of 6 plus, and then 2 divided by the square root of 6. Now this is all well and good. This is perfectly fine, in my opinion. But I'm looking at the answer form they have at Knewton Alta here, and looks like they don't like having, you know, radicals and denominators. So I'm going to rationalize the denominator here, multiply this 2 over the square root of 6 by square root of 6 over square root of 6. And now we have square root of 6 plus, and then 2 root 6 over 6, which is 1/3 the square root of 6. And putting these together, this is 1 and 1/3. Square roots of 6, 1 plus 1/3 is 4/3, right? 1 and 1/3 times the square root of 6. There's the x coordinate of our point when the value of t is, positive square root of 6. And then the y coordinate in a similar fashion, right? Y is given by this equation. When t equals the square root of 6, that would be the square root of 6 minus 2 divided by the square root of 6, which would be very similar to the previous one, right? I would multiply this fraction here by square root of 6 over square root of 6. And we'd have, 1 square root of 6 minus 1/3 square root of 6, and 1 minus 1/3 is 2/3, right? So 2/3 times the square root of 6. So there's 1 point. 4/3 times the square root of 6 for the x coordinate, 2/3 times the square root of 6 for the y coordinate, and I'll box this in. This is one part of the answer. All right, that's one answer. 1 point on our curve, which we'll see. I'm going to go to Desmos, and we'll show that this is actually a point on the curve where we have a tangent line with a slope of 2. And this is one of them. There was this other possible solution as well. T equals, negative square root of 6. It shouldn't be that much more different. So the x coordinate when t is negative square root of 6, you have negative square root of 6 for t, plus 2 over negative root 6. That'll be minus then, minus 2 over the square root of 6. And so this is having, negative 1 minus, and this will become 1/3, right? Just like earlier, 1/3 the square root of 6. So that's negative 4/3 times the square root of 6 for the x coordinate. And then the y coordinate when t is negative square root of 6 would be negative square root of 6. And then minus 2 over negative root 6 would be plus 2 over square root of 6. And it'd be, negative 1 plus 1/3, right? Negative 1 root 6, and this is once again 1/3 root 6. So this is negative 2/3 times the square root of 6. So pretty similar, just on the this is a quadrant 1 point where x and y are positive, and we just get the opposing, quadrant 3 point where x and y are both negative, just kind of reflecting this across the origin. So the other point on the curve where, it has a slope of 2, the slope of the tangent would be 2, has an x coordinate of negative 4/3 times the square root of 6, and a y coordinate of negative 2/3 times the square root of 6. And that is it. We'll see this visually. I'm going to verify this visually, all right, at desmos.com. But these are what we're looking for. These 2 points are on this curve, all right, the curve defined by the parametric equations, and they should be points where the slope of the tangent to the curve is 2, positive 2. Right. You can see that those are the answers too when I go back to the site, right? You see one of them has, the first and second blanks are for one point with the negative 4/3 root 6, negative 2/3 root 6, and then the third and fourth blank are for another point with the positive 4/3 root 6 and the positive 2/3 root 6, right? So I got them. Now let's verify this visually. I also like to, as often as I can, it's not always possible or easy to do, but as often as I can, I like to verify things visually. So desmos.com, free online graphing calculator. I'm going to enter the parametric equations for our curve. Now, to enter parametric equations in Desmos, you have to enter it as an ordered pair. So left parentheses, and then the x coordinate in terms of t was t plus 2 divided by t. Then comma, and the y coordinate in terms of t was t minus 2 divided by t. Right, and once you do that, it automatically sets up a range of 0 to 1 for t. I'm going to change this to just negative 10 to 10. Right. And look, we get it looks like a hyperbola, right? And you could eliminate the parameter and get an equation involving just x and y, a rectangular equation for this. That would be in a I'm sure you could eventually get it into a hyperbolic form. But we're not asked to do that, right? You could do that, but you're not asked to. Now I also want to put up the points that we just saw, right? We found these points. I'll just put up the ordered pairs. One of them was, 4 times the square root of 6 divided by 3, 4/3 the square root of 6, comma, and then 2 times the square root of 6 divided by 3. So there's one point. Label it, right? It's got the decimals and all that, but there's a point on the curve, and it's clearly on the curve. I hope you see that. It is on this curve traced out by those parametric equations. And without doing much of anything, you can see that this point on this curve, the curve is pointing in a direction that's up and to the right. It definitely has a tangent line with a positive slope, and it should be positive 2, right? And let me show you, let me graph the line with a slope of 2. That would be tangent there. So I'm just going to put it in point slope form. So y minus 2 square root of 6 divided by 3, y minus the y coordinate of our point equals the slope. And we said the slope should be 2 times the quantity, and then x minus the x coordinate of our point, 4 square root of 6 divided by 3. Right? And look at that line that just popped up there. Maybe I'll make it a dashed line in settings, and hopefully it's obvious, right? Hopefully it's clear to see that the closer I zoom into that point, the better and better the line is to approximating that curve, right? That dashed line is definitely pointing in the direction that the curve is going in at that moment. So it is tangent, right? Great, so that is definitely a point that has a slope of 2, right? Where the curve has a slope of 2. All right, then I'm just going to do a relabeling here. The other one had negative 4/3 square root of 6 and negative 2/3 square root of 6. So there it is there on this other branch of the hyperbola where my cursor's floating over. And again, it's on a point where, you can see that the curve is going up to the right at that moment. So the tangent line should have a positive slope, and I'm hoping that it's positive 2. And all I'm going to need to do here is change these minuses to a plus in the equation for the line. Y minus negative 2/3 root 6 would be y plus 2/3 root 6 equals the slope 2 times x minus negative 4/3 root 6, which would be x plus. And there you go. All right, see this other line with a slope of 2 that is definitely tangent to the curve at the point mentioned. right? The closer I zoom into that point, the better the line looks to approximating the curve. That line is clearly pointing in the direction that the curve is going in at that moment. All right, so the curve has a slope of 2 at that point. All right, so both these points that I found on paper by hand and you see in here, and you saw in Desmos, are definitely the points of this curve where the curve has a slope of 2. The slope of the tangent is 2. Wonderful. All right, and that's it for this. Again, hopefully watching me do this here helps you out with all the problems in this same objective that are quite similar, right? You find the dy over dx, set it equal to whatever number we were talking about. Here it was 2. Find the values of t, plug those values of t into the parametric equations to find your points. And thank you very much for watching.